In a previous video, we looked at L'Hopital's rule and also some examples where we already have expressions that are in indeterminate forms and we directly apply L'Hopital's rule to find the limits of those expressions when they exist. And if you want a review of L'Hopital's rule specifically, I've put a link of that video in the description to this one. Now, just kind of verbalizing it, L'Hopital's rule says that if you have the limit as x approaches a value of a ratio of two expressions, and the limit of the numerator and the limit of the denominator, when you look at those limits individually, you get either 0 over 0, infinity over infinity, or any of the negatives associated within that infinity over infinity case, then the limit as x approaches the value of the original ratio will be the same limit as x approaches the value of the derivative of the numerator, thought of as a separate function, and the derivative of the denominator, when the limit exists. Now there are other expressions that I'm doing examples of here that aren't indeterminate form at the very beginning, and so we can't use L'Hopital's rule right away. But when we work with applying properties and mathematical operations to the expressions, they transition into an indeterminate form, and we can use L'Hopital's rule at that stage. Let's look at these examples. So the first one is the limit as x approaches 1 from the right of 1 over the natural log of x minus 1 over x minus 1. So I want to just think about what are these limits approaching to see if it's one that I just have my basic properties of limits and I can just evaluate it directly, or maybe it's one of these cases that I have to work with a little bit more. Well, as x approaches 1 from the right, the natural log of something approaching 1 approaches 0. And 1 divided by a value that approaches 0 approaches infinity. Then I have a subtraction. And then also, as x approaches 1 from the right, a number that's approaching 1 from the larger side coming into it, like 1.01, 1.001, etc. Subtract 1 gives me a small number here, and 1 divided by a very small number getting smaller and smaller, that fractional value goes off to infinity. So this is an infinity minus infinity case. Now with these, oftentimes what you do to work through these to transition the expression is you actually get common denominators and just put the fractions together. So I have the limit as x approaches 1 on the right of, and we just want to look at the lowest common denominator between these two fractions actually is the natural log of x factor and the factor x minus 1. So build this first fraction top and bottom by x minus 1. And then build the second fraction top and bottom by the natural log of x. And now do the arithmetic across the numerator and keep that common denominator. So we're just using our properties of fractions for that part. Now, as x approaches 1 from the right, a value approaching 1 subtract 1 approaches 0, and then the natural log of a value approaching 1 approaches 0. So I have 0 minus 0, or 0 in the numerator, and thinking individually in the denominator, as x approaches 1, something approaching 1 minus 1 approaches 0, and the natural log of something approaching 1 approaches 0. So I have also a 0 in the denominator. So this is indeterminate form. So this is the expression that we can use L'Hopital's rule in. So now my limit as x approaches 1 from the right, take the derivative of the numerator separate from the derivative of the denominator for the application of L'Hopital's rule to help us find the limits of indeterminate forms. Now, at first you might be thinking, wait, didn't I do something different with fractions when I was differentiating? If you have a function that is a ratio of two functions, and it just asks you to find the derivative of that, then you do have to use the quotient rule on that. But that's not what we're doing here. Here, we're trying to find the limit as x approaches a value of a ratio of two functions that they are indeterminate form. And if that happens, L'Hopital's rule says that that limit of the ratio of the two functions as x approaches the value is going to be the same as the limit as x approaches the value of the ratio of the individual derivatives. So that's why we're doing the process this way, because of its application from what L'Hopital's rule says. So now we have, in our numerator, the derivative of x is 1, the derivative of -1 is 0, and the derivative of our the natural log of x, well, that's 1 over x. Now in the denominator, I have a multiplication here. So I could either distribute the natural log and then take the derivative of that, which still is going to have a product in it, or I can take the derivative using the product rule where x minus 1 is a factor and the natural log of x is a factor. So since I already differentiated the numerator, I do want to differentiate it for the example I'm giving you. But again, if you worked off to the side and distributed first and then differentiated, you'd see we'd get the same thing. So my first factor is x minus 1. My second factor is the natural log of x. By using the product rule, it's the first factor times the derivative of the second factor, and the derivative of the natural log of x is 1 over x, plus the derivative of the first factor. The derivative of x minus 1 is 1 minus 0, which is just 1, then times the natural log of x. Now we're going to simplify this. The first thing I'm going to do is I'm going to rewrite the denominator without parentheses. So I have 1 minus 1 over x over x times 1 over x is 1, -1 times 1 over x is minus 1 over x, and then plus the natural log of x. Now before I look to see what's happening, I'm going to go ahead and multiply top and bottom of this fraction by x to remove the complex fractions. So top and bottom by x is really just multiplying that overall fraction by 1. So this is the limit as x approaches 1 from the right of x minus x times 1 over x is 1, then over x minus 1 plus x times the natural log of x. Now as x approaches 1 from the right, x minus 1 still approaches 0, and I still get a 0 in the denominator as well. So approaching 1 minus 1, and then approaching 0, so that whole thing approaches 0. I have indeterminate form again, so I can use L'Hopital's rule again. So this is the limit as x approaches 1 from the right. The derivative of x is 1. The derivative of the constant term 1 is 0. And then now in the denominator, the derivative of x is 1. The derivative of the constant term, -1, is 0. And then the derivative of the natural log of x is 1 over x. And then when I look at this as x approaches 1, I have 1 in the numerator. And then in the denominator, I have 1 plus, well, 1 divided by a number approaching 1 is 1. So 1 plus 1 down there is 2. So I get a limit of this as x approaches 1 from the right of 1 over the natural log of x minus 1 over x minus 1 is equal to 1/2. How about the next one? This is the limit as x approaches infinity of 7 times e to the negative x times the cubed root of x squared. Well, we have our information as x approaches infinity, 7 approaches 7, e to the negative x, think e to the negative 10, e to the negative 100, e to the negative 1,000. That approaches 0 times, and then the cubed root of x squared as x gets infinitely big. Well, you take something getting infinitely big and square it, that's even larger still. And even when you take the cubed root of that, it'll still continue to grow. So that goes off to infinity. So it's this case. Now I want to again write this as a fraction. So I want to look at this expression and see which of the factors would be the easiest to not only put into the denominator, but also to differentiate once it's down there. So if you think about this as that expression over 1, and it's all attached by multiplication, I'm going to leave the 7 in the numerator. This e to the negative x, I'm going to move into the denominator, and when you move that exponential expression into the denominator, you change the sign of the exponent. So if it's e to the negative x in the numerator, it's e to the positive x in the denominator. And then the cubed root of x squared we're going to write as x to the 2/3 power. So now evaluating it, my numerator goes off to infinity. My denominator now is e to the positive x, and as x approaches infinity, e to the approaching infinity power also goes off to infinity. So here's one of our indeterminate forms that L'Hopital's rule can be used on. So then I have the limit as x approaches infinity of, take the derivative of the numerator, think of this 7 as 7 over 1. So when you take the exponent and multiply it to the coefficient, 7 over 1 times 2/3 is 14/3. X to the subtract 1 from the exponent. So 2/3 subtract 1 is a negative 1/3. Then divided by the derivative of e to the x is e to the x. E to the x is its own derivative. Now rewriting this x to the negative 1/3, I'm going to take it down in the denominator and it changes the sign of the exponent. So I have the limit as x approaches infinity of 14/3 over e to the x times x to the 1/3. And I could multiply this top and bottom by 3 to get rid of this complex fraction, but I don't have to do that in order to think about what this limiting value is going to be. So my numerator of my overall fraction is 14/3. It's a fixed number. There's no variable there. So I have a fixed number in the numerator. In the denominator, I have e to a power that's getting infinitely big. So that factor in the denominator is getting infinitely big. And the cubed root of a number getting infinitely big is also getting infinitely big. So I have my 14/3 over something going off to infinity. So if your numerator is fixed and the denominator is getting extremely big, like 14/3 divided by 1,000, 14/3 divided by 1,000,000,000, the fraction is going to 0. And so this limit that we originally started with, that's going off to 0. Okay, last one. This is the limit as x approaches 0 on the right of x to the cubed root of x squared power. So when I'm looking at this, I have a letter base and a letter exponent. These we actually have to find a limit of a kind of associated expression and then transition it back. So as x approaches 0, the base is approaching 0, and the numerator, the square of a number getting extremely little on the right-hand side, gets closest, approaches 0. So as x approaches 0 on the right-hand side, x squared approaches 0, and the cubed root of something approaching 0 approaches 0. And I have this as a 0 to the 0 power. Again, one of my cases. And if it had been a base approaching 1 to a power that's approaching infinity, you would treat it very similarly to this one. Okay, now because we have a variable base and a variable exponent, we actually want to look at what if we have y is equal to that as x approaches 0 from the right of our x to the 2/3 power. And remember, when I have a radical notation, the index of the radical is the denominator of the exponent, and the power is the numerator of the exponent. And I want to look at what I'm asked to find. I just called that y. And now I'll take the natural log of both sides. And the natural log of the limit, as long as this limit exists, is the limit of the natural log. So I have the natural log of y is equal to the limit as x approaches 0 on the right of the natural log of x to the 2/3 power. Now, I'm going to look at just this right-hand side for a while and then bring it back to that part of the equation to finish the process out. A lot of times they suggest that you bring each of the sides down, and you could do that or just work on the expression and put that back on that side. The process that gets a little bit tenuous here is just remember that you still have to transition it back. So now I have the limit as x approaches 0 on the right of my natural log of x to the 2/3 power. But now I can use my properties of logs, and properties of logs of a base to a power says you can bring the power down as a factor. So I have the limit as x approaches 0 on the right of x to the 2/3 times the natural log of x. When I look at what's happening with this, as x approaches 0 on the right, I have something approaching 0 to the 2/3 power approaches 0, and something approaching 0 on the right of the natural log of that. So natural log of something approaching 0 on the right approaches negative infinity. So I have this case. Now remember, we want to change it into a fraction, and we want to take the factor in the denominator that would be the easiest to move as well as the easiest to differentiate it once it gets down there. So we are going to look at this as the limit as x approaches 0 on the right of, we're going to take this x to the 2/3 in the numerator, and when we take it in the denominator of the fraction, it's an x to the negative 2/3. And then leave the natural log of x in the numerator. And now I have negative infinity over infinity. I have a case that I can use L'Hopital's rule. Take the derivative of both the numerator and denominator. This is the limit as x approaches 0 on the right of derivative of natural log of x is 1 over x. And the derivative of x to the negative 2/3 is negative 2/3 x to the negative 2/3 minus 1 is a negative 5/3. Now when I simplify this, I have the limit as x approaches 0 on the right. I have my 1 over x numerator, and I'm going to multiply it by the reciprocal of this fraction that's in the denominator. So this denominator right now is a negative 2 in the numerator, and in the denominator is 3x to the 5/3. Put it down in the denominator, that little fraction, it changes the sign of the exponent. So as I do that, I get a 3x to the 5/3 in the numerator, and I get a negative 2 in the denominator. And then that gives me the limit as x approaches 0 on the right, and when I simplify this, it's a negative 3x to the 2/3 all over 2. Dividing exponential expressions, keep the base and subtract the exponents. So 5/3 minus 1 is 2/3. Now think of that. As x approaches 0 from the right, x to the 2/3 approaches 0. So a constant times 0 is 0. This limit is 0. But that's the natural log of what we're looking for. The natural log of what we're looking for is 0. To find out what y is, we want to go from logarithmic form to exponential form. So natural log, our base is e. So the exponent you put on e to get y is an exponent of 0. So e to the 0 is y, and e to the 0 value is 1. So this limit is 1. So hopefully these examples helped you get a little stronger foundation to find limits of expressions that when you rewrite them actually transition into equivalent expressions of indeterminate form, and then you can use L'Hopital's rule to finish out and find the limit.